All right, good morning, everybody. So, I want to talk about makefiles today. Um, Makefiles will be a definite big chunk of the grade on your next programming assignment, which I plan to post probably tomorrow. Um, so this is important stuff. Um, the basic setup is we're going to be developing C programs that may have multiple pieces to them. And a lot of times we want to put those different pieces into different files. So we'll take apart a program and do this in a few minutes. Um, in the end, you're left with a bunch of files which will eventually get combined together to create an executable. And there's things that we might need to put in all of these files. For example, function prototypes. We might have a function that we use in all three of these files, and we might need to say, integer, my function, parentheses, int, comma, char star, right? And those things that we're going to include in all of these files, we might put in a separate .h file, which we number sign include in these. We'll play around with that in a few minutes too. All right. When you're writing your program and you're breaking it up in this way, you know how to build an executable program. But if you're going to take this collection of code and push it out to the web, for example, and other people are going to download it and want to build this program and then want to make changes to it, they don't have your knowledge of how all these things go together to create an executable. So here's the idea. We know that we can just compile everything, right? We can always say gcc-o main star.c. And there's a good chance that will get us what we want, right? But maybe we have some .c files in here that we don't want compiled in. And maybe we need to explicitly list all of these files. But this is inefficient, okay? If this is what your makefile looks like on your next assignment, you won't get any points for it. This is not an efficient way to build an executable. So we want to be very tactical in how we put together our source files to make an executable. And here's the idea. Suppose that we make one change to this file, f2.c. If we do this, we're not only recompiling f2.c, but also f3 and f1 and f. We're recompiling all of our source code, when in fact, the source code only changed in one file. So our setup is we're going to compile these into objects, which are .o's. We're not going to compile the .h file. That doesn't make any sense. The .h is included in the .c's. But we're going to compile these .c files into objects and link those together with something like this, but not exactly. All right, now if we make a change to this one file, what do we have to do? We have to recompile that. And the -c switch says just make an object file. So this will rebuild f2.c into f2.o, and then we do this, which links all of those objects together. And then if you come along and you change f1.c, you compile f1.c to an object, you link your objects. Now, if you make a change to f.h, which is included in all three of these, you need to remember, hey, I've got to recompile all three of these files to objects and then link everything together. So that's a lot of expertise. And if you're building the program yourself, you know how to do this. If you come back to it in 6 months, maybe you forget. But if somebody else is working with this, they don't know that level of understanding that you have. So what we want to do is take all this information about if something changes, what has to get recompiled, what has to get relinked. We're going to put that in a very systematic form. And the form is called a makefile. And a makefile is really just a recipe for building an executable, typically out of source files. Let's see, question, does the H file need the function prototype, or do the function definitions have to be in that file as well? Typically in a .h file, there's no actual runnable code. Okay, typically what we put in here are function prototypes, constants like pound defines, maybe some includes, structure statements, and that's probably about it for us. If I write a function that takes a string and counts how many letter E's there are in it, that does not belong in a .h file. Okay, that belongs in a .c file. Any runnable code goes in a .c file. But statements that I would typically write in multiple files, those statements can go in a .h. Function prototypes are the main thing that we're going to use that for right now. Later courses, when we're working with structures, definitions of structures, type defs, those things will go in a .h also. All right, so let's do this with specifics and work through these steps. So here's a program we've played with before, right? So it doesn't really do anything useful, but imagine this is really long and really complex and really useful, and you've got a lot of people working on this code. All right, so what does this do? There's an include for standard I/O because we're doing some input and output. There's a character array, there's an integer. There's a welcome message or some kind of initialization, okay? And then there's a loop here, right? So we print out a prompt for the user, we read a line of input, and then we go into a loop, which says let's read a line from the user, scan it, and if it's not scannable as an integer, print a message saying bad number, try again, and ask them to put in another line. And then when we get out of this loop, we know that the scanf did return a 1, so I is the integer that the person typed in, and now we can print out the square of I is, and we'll just print out I squared. All right, so this is just sample code. So if you don't type in a number, if you just hit enter, if you type something weird, right, it does that. But if you type in a number, then it says the square of 7 is 49. All right, so that's our first main program. And everything is one file, and everything is one function, right? So if this initialization was big and complex, and the main loop was big and complex, and so on, this would get difficult to manage. So what we do is we start breaking this up into functions. This is what I call modularizing, breaking into modules. So now I have something called greeting, get num, and print result. Okay, we prototype the functions up here so that the compiler knows greeting doesn't take any arguments, get num returns an int, and so on. And my main program is really simple now. Print out a greeting, get a number, save that in I, print the result. And my greeting, I made a little fancier, prints out 4 lines of text. And my get number has all of that logic for prompting, reading a line from the user, trying to scan it, and looping repeatedly if the user's input was not a valid integer. And then returning the integer at the end here. And so remember up here when I say I equals get num, that says call this function get num, execute all the instructions in there, come out of that function after a return statement, and whatever value was returned, set I equal to that. So in this case, I would get set equal to what turned out to be I in this function, but it could have been called anything. And then print result takes an argument and just prints it out and prints its square. All right, so that's a little better. That's its own set of functions that do our task. But the non-ideal thing about this is everything is still in one file. This is all in main2.c. And if I change one thing in here, like I decide to have only 3 lines, I've got to recompile all this code. I recompile the main program. I recompile the greeting, which I have to. I recompile get num. I recompile print results. Okay, that's the inefficiency that we're after right now. We changed one function, greeting. All we should have to do is recompile these lines of code. Okay, this will make our development a lot faster. So what I'm going to do is I'm going to split this into multiple files. So So I'm going to make a file called main3, a file called greeting, a file called getNum, and a file called printResult. Alright, so I'm going to VI all of those. So getNum is going to need standard I/O, and it's just going to do this. Alright, that's my getNum function. It needs standard I/O because it's doing printfs and fgets and scans. But it will not take any arguments. It will run this code until it finds a valid integer from the user, and then it'll return it right here. So that's our whole getNum function. The greeting function, well, that also needs standard I/O because it's doing prints. But that's all it's going to be, right? So this is the whole greeting. And our main program is called main3. And I'll come back to that one in a second. Let's do printResult. Now I don't need to prototype these functions, right? Because nothing in this file is calling printResult. The only thing in here is a definition of what printResult is, the actual code for it. So it would be silly to prototype it. It wouldn't do any harm, but there's no need for it. Just like in getNum, there's nothing in here that calls getNum, so I don't need a prototype, but I could have it. Alright, so let's look at our main program, which is main3. And that's all I need. Just these calls to these functions. Now nowhere in this file, when I try to compile this main3, there's nowhere in here where the function greeting is written, right? But that doesn't bother the compiler because it's seen a prototype for it. It knows enough about this function. It knows it takes no arguments and it returns no value. And that's all it needs to be able to compile this. Down here, it doesn't know what getNum does. It doesn't see the code for that. It doesn't know it does scanfs and all that kind of stuff. But all it needs to know is that it takes no arguments and it returns an integer. And that's enough to compile this line of C code into assembly language, which says call this function, take the return value, save it in I. Alright, so the prototypes are giving the compiler enough information that we can write something like this without actually writing getNum or greeting or printResult. And we do this already, right? We never actually write code for fgets. We never write code for scanf or printf. That code is provided for us somewhere else. But the compiler knows what printf is because it's prototyped in this include file. Alright, so I'm going to do one more thing. I'm going to make a new file, an include file. And I'm going to put these includes up here. I'm going to put in the include for standard I/O. And I'm going to put in these three function prototypes. Actually, I'm not going to put standard I/O. That's personal preference. I'm just going to put the function prototypes in here. And so now, instead of putting those function declarations in here, I can say include quote main3.h. Alright, so what happens when I run my program? The C preprocessor runs first, and it looks at these statements that begin with a number sign, and it does something. What it's going to do at this point is it's going to look in my current directory for a main3.h. It's going to find it, and it's going to basically read the contents of that file into this spot in my program. Now, if I use angle brackets, it's not going to look in my current directory. So angle brackets say look in a very specific directory called /user/include. Quotation marks mean don't go into that special directory, just look wherever I tell you. So if I just say main3.h, it's going to look basically in my current directory for a main3.h. if I said include /home/nick/something, it would look in /home/nick for a file called something. So this is a very specific path. With the angle brackets, it's probably looking for /user/include/standardIO.h. But the angle brackets are there so we don't have to keep typing this over and over and over again, because then it would look like C++ or something. Alright, so this is a really, really small main program now, right? And as a main program, this file really tells you what's going on, right? I'm including something that's just, you know, support for all of this, but what's my main program? Print a greeting, get a number, print a result based on that number. Alright, so let's make this thing work. So I have 4 C files: get num, greeting, print result, and main3. I'm going to move into a new directory. Alright, so I'm in a new directory, and this is typically the stuff that you would put in a Git repo or a tarball or something that you would use to distribute this to other people. And it's all source code. Right? It's all printable stuff. And we want to compile it. Okay, so here's one way to compile this. gcc-o main3 star.c. That'll definitely work. And it's created one additional file now, main3. That's the executable, and if I run it, you know, I can misbehave and type in weird numbers, and then when I type in a number, it prints out the number in the square. So it does the same thing that the original program did. But again, this is not an ideal way to build this. So let's say I modify greeting, and I take this out so it only greets me once. If I recompile, it's recompiling all of my C files. Alright, so here's the more nuanced way to do this. Compile each of these into an object file. And now I've got, for each C file, I've got a .o file. And those objects can now be linked together to create our executable. Alright, but now here's the good part. If I change one file, like my greeting.c, I recompile that one .c file, and then I relink all my objects together again. And I did not recompile getNum or main3 or print result. Someone just asked why I prefer a monochrome terminal. I have 2 colors on here. I have black and green. It's not monochrome. That's a discussion for another time. Personal preference, habits, but it works for me. We can talk about it sometime. Alright, so this is what we're after, okay? What we want to know is, for example, if I change main3.h, what else do I need to change? Say I want print result to take a float instead of an int. I would need to know which files are including main3.h. Well, it turns out just main3.c includes it. So if I change main3.h, I would need to recompile main3.c and then link everything together. Alright, so let's talk about makefiles now. And yeah, this is definitely more important when compiling takes a long time. For us, it's really just kind of an academic exercise. But we're in school, right? So that's what a lot of things are. But if it's taking you, 12 hours to compile your entire collection of C code, and you change one file, you don't want to spend 12 hours compiling that just to test it and find out that, you did something wrong in there. You really want to just compile the smallest amount possible and then link things together. Linking is a lot faster than compiling. And yeah, compiling can take several hours. I mean, it depends how much stuff you have. So if you're building a Linux system and you've got, 50,000 C files, you're not going to recompile each of those each time that you make a change. All right, so let's talk about a makefile. So makefiles are usually called makefile. It's a plain text file. It's something you create with just a standard editor. And it's really pairs of lines that basically all together give you a description of how to build, in our case, an executable. And so each line looks like this. There's a target, okay, the thing that you're trying to build. And then there's dependencies. All the things that need to be up to date to build this target. And then on the next line there's a tab, and it's got to be a tab in the beginning, it can't be spaces. There's a tab followed by a recipe. And the recipe basically says, assuming all these dependencies are up to date, how do I build this target? And there's just pairs of these. On and on and on. And so we're going to describe all of the interdependencies of our files, all the commands that need to be used to build the different pieces of our project, including the final executable. All right, so let's put this together and then let's take it apart. So here's my makefile. So my main goal is to make main3. And this depends on the following files: main3.o, getNum.o, printResult.o. I really cannot spell or type. And greeting.o. If I didn't know what that was, I could say :r exclamation mark to say execute the command ls*.o and then read that into my file, and that would have given me this, and I could join these together with a J and then type main3 in the beginning. VI is your friend. Alright, so these are the 4 files that need to be up to date in order to build main3, and that's really all I care about. I'm not going to say that main3 is dependent on my include file, my .h file, because if the .h file changes, somewhere in here I'm going to describe that greeting.o will be out of date, or main3.o will be out of date. All right, so let's put this together and then we'll talk about it. Now, supposing that all of these dependencies are satisfied, how do I build main3? gcc-o main3 main. Well, and I will do my trick again. Actually, I'll just cheat and go like this. All right. If you say :set list, it will show you unprintable characters, and I can see my Control-I in the beginning here. That's the character for a tab. It's ASCII character 9. You can also see where each line ends. There's a little $sign there. And I can set NL for no list. To take that out. All right, so there's the part of my makefile that describes how to build main3. right? But if these .o files don't exist, there's nothing in here that says where do those .o files come from. All right, so let's remove these .o's from my directory, and let's remove main3. So I've got my source files, including my .h include file, and I've got a make file. Okay, the way that I execute the make file is I just use the command make. And when you say make, the program make will look in your current directory for a file called makefile. And if it finds it, it will look inside and it will try to build the first target that it finds. So whatever you name in the very first line of your makefile, that's what it's going to try to build. I could also say make and I could name a target specifically. So I'm just going to say make. And it's going to say, Alright, so this is a bit of a problem because make is actually a little too smart for us. It thinks that it knows how to make these .o files for us. And so it's using the cc command instead of gcc and stuff like that. So, yeah, w implicit is a thing. Okay, so rather than showing you what not to do, let me go ahead and continue describing this make file. So we need to tell it how to make main3.o. Okay, so I'm going to put in a target for here for main3.o. And main3.o actually depends on two things, main3.c and main3.h. If either of these things change, we've got to rebuild main3.o, potentially. Right? Because the C file includes the .h, so if the .h file changes, then effectively the contents of this changes, which means when we compile it, the .o might change. All right. Now, if both of those dependencies are satisfied, here's how we build main3.o, just gcc-c main3.c. Again, we do not compile main3.h. .h files don't include executable code. They're function prototypes. Compiling that would say something like, you know, make a main3.o maybe. That doesn't do anything. We include standard.io.h. We don't compile standard.io.h. You don't say gcc main.c standard.io.h, right? So don't compile your .h files, but list them as dependencies. All right. We also need to tell it how to create getNum.o, which depends only on getNum.c. And we're going to have to do this for print result. And we're going to have to do this for greeting. And I'm using n to search for things, and I'm using dot to repeat the last command there. So that's why I'm changing those quickly. So this is starting to look like a legitimate makefile, right? To build main3, which is my goal, I need these 4 object files. .o files are called object files. And each of those .o files, there's a description of what it depends on and how to build it. So if the greeting.c file changes, make will look at this recipe and say, okay, well, to build main3, I need greeting.o. Is greeting.o up to date? Let me check. What does greeting.o depend in? It depends on greeting.c. It will look at the timestamps on greeting.o and greeting.c. And it will say, hey, this file is newer than that file. Which means the C file on which the O file depends has changed. So I better rebuild this. So we'll go ahead and execute this command. And now we will check again, and it will see that this thing has an older timestamp than that, so greeting.o is up to date. And it'll do that for each of these things that main3 depends on. And once all of those are satisfied, then it'll execute this statement, build our executable. Alright, so let me get rid of my .o files again. And let me get rid of main3. So I have my 4 C files, my included.h file, and my make file. And if I just say make, it will go ahead and call gcc-c on my 4.c files, and then it will put those together and make my main3. Now I'm getting a warning here, right? And the warning is that in main3.c, I didn't say int. So I'm going to declare this to be an integer. Alright. Do I have to recompile everything now just because I changed main3.c? I don't know. I'm just going to say make. And all it's going to do is recompile main3.c. And then it's going to link all my objects together. And there's my executable main3. And that works great. Alright, so let's just play around with using this. So I'm going to edit greeting.c, and I'm going to shout. Alright, got to recompile it, just say make. And it will figure out what it has to do, and it'll do it. So in this case, it compiled greeting.c, and then it linked everything together. And now when I run my program, it shouts at me. Now if I say make again, it tells me main3 is up to date. There's nothing to do. If main3 gets deleted, I say make, it just compiles my objects together. If my getNum.o disappears for some reason and I say make, it'll recompile getNum.c and then link my objects together. So now you never have to type GCC again, right? Every time that you make edits and you want to run your program, the first time you just have to say make. And it'll do all the stuff to make your executable. And you don't have to keep saying make, right? When I want to run my program, I just say name of the program and it runs. But if I change something, then I have to say make again. If I'm not sure, I can say make anyway and it'll tell me, oh yeah, it's up to date. Alright, let's change the .h file. Let's print this out as a character. That'll be weird. So I'm going to change my .h file, and I'm going to change print result to take a character. This is a horrible example because it's going to generate all kinds of errors, but I'm just interested in what gets compiled. Okay, I changed print result, I changed my .h file. What does make end up doing? It recompiles my main3 because it has an include that changed. It recompiles print result because the code for that actually changed, and it links my objects together. And of course this will do really weird stuff. This will print out like a tab and an @ sign. Oh, I printed it as a %d. Never mind, that's fine. But I can blow it up. All right, so this is what we're after, okay? Something that very precisely describes all of your dependencies. And if you change your dependencies, if you create a new file, if you decide that you need to include main3.h in another file, right, then you need to update your makefile accordingly. So right now everything is up to date. Let's change this, and let's just suppose that getNum.o also depends on my include file. It doesn't, but let's suppose for some reason I had something in there, a define or something, that I wanted to include. Well, if I say make, now it recompiles getNum.c and it links my objects together. Now we can do anything we want with these makefiles. What I've shown you is sort of a typical use case where we're using this to to build an executable out of C source code. But we can do anything we want. If we do text processing with LaTeX, for example, we can put all the commands that we use for that inside a makefile. If we do something with files where we download them and we run them through some sort of text processing and sort them and do something else, we could put all of that in a makefile, right? It's really a general utility. And, you know, big long web page, doc page that tells you all about it. And I think O'Reilly makes, you know, a whole book on make. All right, let's see. If we set our tab stop to a smaller value, we still need only one tab in our makefiles. Yeah, you only need one tab. If you're changing your tab stop in VI, yeah, as long as it's not changing it to spaces, you're okay. Just make sure it's actually a tab character. And like I say, you can say :set space list to see those characters, or XXD it. And if you XXD this, you will see main3.o dot right there. That's a tab character, character 9. So this is all that first line of my makefile. 0A is a new line. That's the, you know, \n at the end of the first line, and then the 09 is the tab in the beginning of the second line, which was the recipe for making main3. All right. Well, this works great for the most part. So what you might do, for example, is tar all this stuff together. We'll talk about tar files later on. They're mentioned in that quick start guide on Canvas. But you can make a tar file. It's kind of like a zip file, but it remembers everything. And you might, you know, put this tar file somewhere, probably gzip it, and people could download this and then, you know, compile your code and run it on their system. So let's make a new work directory. And let's suppose I just downloaded this all.tar file. So we can look at the contents, so tar tvf, and there's what's in there, so I can extract this. And bingo, I've got a copy of all your work, right? And I'm sitting on a Raspberry Pi, right? And so I want to run your code, and so I say make, and it tells me main3 is up to date. And the problem is that, you know, the dates for all of these things, main3 was created after, you know, all the things that it depended on had changed and so on. It thinks that I don't have to recompile. But if I'm on a different machine, like a Raspberry Pi instead of an x86, and I try to run main3, it's not going to work. So the correct response here is that when you make these repositories of code to share with other people, usually you don't include object files, you don't include executable files. 1, because they take space, 2, because they're not portable, and 3, because they're needless. If you have source files and a makefile, you're probably good to go. But nonetheless, the person who made this tar file, it's me, kind of messed up and included these things, and now when I try to make my file, you know, it's telling me that everything's all up to date. So now I have to go through here and I have to look at all the things that need to get recompiled. So I'm looking at the makefile and trying to figure this out, and this is a mess, okay? And these makefiles get to be thousands of lines long for large projects, and they're write once, read never in a lot of cases. You use them, but to try to go into somebody else's makefile and figure out what it's doing is a whole exercise in itself. So what we would like to do is modify our makefile. So let me go back to my work more directory. What we'd like to do is add something else to our makefile. We're going to put in a way to automatically get rid of all the stuff that got created by the makefile. It's appropriate for me to do that because I'm the one who made this project. I'm the one who understands all of the dependencies and so on. So we're going to do something something kind of bogus. Remember, you can do anything you want with these makefiles. So I'm going to create a new target. And this is typically called clean. And clean, I'm not going to list any dependencies on it. And I'm going to say, if you want to make clean, there's no dependencies you have to satisfy. Here's the command you use. I'm going to say rm main3.o, well, let's just remove all of these things. All right. So there's no compiling going on here. There's nothing actually being made. I'm not creating a file called clean. This is kind of a trick. If I say make clean, it's going to look for a target named clean, and it's going to find one right here. And it's going to say, okay, what does this depend on? It doesn't depend on anything. It's going to go ahead and execute this command. It doesn't realize that this is not building something called clean. It doesn't care. All we're saying is that if someone wants to make clean, execute this command. Now I could rm star.o, but the problem to that is that somebody who's working with this code might have made their own object files and don't necessarily want those to get clobbered when they try to clean up what they downloaded. That would be a dangerous thing to do anyway, but you know, generally we don't want to just remove wildcarded stuff, especially if they have, you know, directories or links or things like that. All right, so the typical way we do this, right now I've got some object files, I've got my main3. If I try to make, it tells me everything's up to date. I'm going to say make clean. And it's showing me what it's doing, it's removing those files, and now if I look, all I've got is my source files again. And if I say make, everything gets rebuilt, recompiles all my C code, and then makes my executable. And yeah, this is what we were trying to avoid, was having to do this. But the first time that you build a project, often you want to rebuild everything from source code. Okay, or if you move to a new system, if you upgrade your operating system, if you go to a different CPU architecture, something like that, you may want to actually recompile everything. So I can say make, and I can go out and I can get a cup of coffee and have some lunch and go for a run and come back in a few hours, and it will be doing all of the compiling and everything that it needs to do. And then when you're done, you've got your executable program and you're good to go. All right, let me show you an example of a poor makefile. All right, this will work, but this will not get you points on a programming assignment. All right, it's technically correct. To build main3, I need to have updated versions of all of these .c files. And if any of these .c files change, I need to rebuild main3. And how do I build main3? I recompile all of my .c files into an executable. All right, so if I have just my source files and my .c file, and I say make, it recompiles everything. And main3 works fine, right? But this is that original problem that we said we were trying to avoid, which is if I change my greeting and I say make, it's recompiling main3.c, getNum.c, printResult.c, as well as greeting.c. Alright, so this is not the kind of makefile that we want. Technically it works, but it's missing the whole idea of makefiles. So we want something like this. Another thing you'll typically find is an install, which might depend on main3.c. Or just main3. And let's just suppose that for some reason, after we're done building this main3 program, we want to put it in the /temp directory so that other people can get to it. That's not something we would do because /temp is temporary. But now I have a new target called install, and if I say make install, it will look to see if main3 is available and up to date, and if it is, then it will copy it to /temp, and then it'll change the permission bits on it to make it accessible to the world, because my default permission is not going to make it accessible. So I say make install, and it copies it over to /temp, and you can see there it is. And if I change one of my files and I say make install, it's smart enough to realize that to install this thing it needs an up-to-date version of main3, and main3 is not up to date because it depends on main3.0, and main3.0 is not up to date because it depends on main3.h. And so it recompiled main3.h. And I also told it bogusly that getNum depends on main3.h, so it recompiled that, and then it rebuilt main3, and then it did the install. Alright, so this is recursive, okay? If we say make install, it will try to satisfy this dependency. If it's not satisfied, it will go through here and look for a recipe to build main3, which it finds right here. All of these need to be up to date. When it looks at main3.0, it says, well, what does that depend on? It finds this and says that's not up to date, so it executes this. Now main3 is up to date, so it comes back here. What about getNum? Well, getNum depends on .h, so it executes this. Now getNum is up to date. What about printResult? That was already up to date. Greeting was already up to date. All of these things are up to date now, so it executes this recipe to build main3. And now it goes back to where it was in the beginning, which was I was trying to build install, and it depended on main3. Well, now main3 is up to date, so now it can execute the recipe, which copies it into the target area. Right? So this is a little bit like the leaky roof, right? If it's raining, you don't want to go on the roof to fix the roof. If it's not raining, the hole in the roof doesn't bother you, right? So makefiles can be that way. If you're just starting a project, it's easy to compile. You don't want to bother making a makefile. And once you have, 15 files, it's too troublesome to make a makefile at that point because, you've got stuff all over the place. So make your makefiles in the beginning. Okay, when you have 1 or 2 files, it'll be really easy to build this. And then as you add more files to your project, just keep your makefile up to date. And really the kind of joy of being able to edit code and just say make is really nice, right? Once you're there, you have to set it up, but once you have it, it saves you a lot of time. All right, if you download stuff from the web, you'll also see make configs sometimes. Make configs are used to basically set up the makefile depending on what version of the compiler you have, things like that. All right, that's everything you need to know about makefiles for this course. I'll mention them on the next assignment, and that's what we're looking for basically. Cool, have a good afternoon. I will see you tomorrow.